Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. I'm here today with a student request on a kinematics problem, a pair of trains on parallel tracks approaching each other with different speeds, and we want to find out where and when they meet. The problem doesn't specify which train, fast or slow, starts where, so I will work the problem both ways to show you that we get the same solution. So here's our problem scenario. Two locomotives approach each other on parallel tracks. One has a speed of 60 kilometers per hour with respect to the ground, and the other has a speed of 90 kilometers per hour with respect to the ground. If they are initially 8.5 kilometers apart, how long will it be until they reach each other, and where will they meet? And here is a short animation of our situation. So we've got the blue train, which I arbitrarily chose to be the slow train, and the red train is the fast train. And they're going to approach each other on parallel tracks, and they will pass, but at some point they're going to meet, and that's what's marked with the green line. So we need to mark a few important places in our problem situation. We need the starting place of the slow train, the starting place of the fast train, and then the point where they meet. And I'm going to label the starting place of the slow train as 0 meters, and I'm going to label the starting place of our fast train as 8,500 meters. And it's also important to note that I'm going to define the direction that the slow train is moving is going to be my positive direction. So the important question we need to ask is, how do we express the relationship between how far each train has gone and how much time has passed? And in math class, you probably heard or learned the relationship distance equals rate times time. And in physics, we're going to be a little more specific than that. We're going to talk about the displacement, the change in position of each train, which, because each one is moving only in one direction, will in this case be equal to the distance the train has traveled. That change in position will be equal to the train's average velocity. And again, because each train has only one speed in one direction during the time period we're considering, the average velocity will simply be the train's velocity multiplied by the time interval. And I'm going to elaborate a little bit further that change in position is final position minus initial position. And I'm going to make one more rearrangement and then explain why. So I'm going to go ahead and add that initial position to both sides, because now final position equals velocity times time plus initial position looks an awful lot like dependent variable equals slope times independent variable plus an intercept. And in fact, this, actually, let me grab, yeah, that'll work. This does look like y equals mx plus b format, because generating the mathematical model for each train's motion and then plotting them, plotting the two models and getting the intersection of the lines on the graph is the easiest way to solve this problem, and it's my favorite way. But if you don't have access to that, I will show the algebraic way too. So I want to note that this equation right here is, I need to write down a little bit lower, this is actually the mathematical model for constant velocity. And I don't quite have enough room, so I'll abbreviate constant velocity CV. So let's create the models for our two trains. We need to talk about those speeds really quickly. The velocity of the blue train was 60 kilometers per hour. And you can do the conversion to meters per second yourself, but you'll get 16.6 repeating decimal meters per second. And I prefer to keep a few extra decimal places and then round at the end. So I'm going to leave it just like that. And then our velocity of our red train is 90 kilometers per hour, which is 25 meters per second. So now that we've got our speeds in the proper units, although they are velocities because we're going to assign directions, we can go ahead and finish out those models. So the position for our blue train, our slow train, is going to be 16.6 t. And since the intercept, the starting position was 0, I'm just going to leave it off. And then our fast train, the red train, since it's traveling the opposite direction of the blue train, we're going to assign a negative value to its velocity, negative 25t plus 8,500. And as I mentioned, plotting this is my favorite way to solve. So there is our blue train, and I used an online tool called GeoGebra to make these plots so that I could get some nice big screenshots for you. And GeoGebra has some additional graphing calculator tools that are going to be really useful here. And there is the graph for our fast train. And oh no, I lost my cursor. There we go. And just to remind you what those two mathematical models were. And so, again, that graphical method means that if we plotted and found the intersection, which is this point right here, this is going to be a time and position coordinate that's going to tell us when and where the trains meet. And we'll work through the algebraic solution first. So, to complete our algebraic solution, we are going to set the position equations equal to each other. And we'll first solve for time by setting the positions equal to each other. And then we can substitute that back in to get our final position. So the blue train again was that 16.6 t. And our red train was negative 25t plus 8,500. And that's going to give me, oh, let's be a little clever. Since I'm using red and blue, let's do this work in purple because that'll be fun. 41.6 t equals 8,500, and that's going to give me a time of 204 seconds. And now I can take that and substitute it into one of my position time relationships. And I'm going to choose the blue train's relationship because it's going to have the least amount of mathematics to do. I am lazy and like to avoid algebra when possible, believe it or not. So when I substitute, I get 3,400 meters. And it's important to note that this is measured from the blue train starting position or from the slow train starting position. If we had substituted differently, like if we were solving for where we are relative to where the red train started, we would get a different value. And in fact, that's going to be part of solving this the other way. What if I reversed where the train started? And that's going to come up shortly. So now let's see what GeoGebra had to say about the intersection of our lines. We got, no surprise, oops, 204 seconds because we'll round that up, and 3,400 meters. So great news that we got the same thing from plotting as we got algebraically. So we're saying that point right there is 204 seconds, 3,400 meters from where the blue train started. So I arbitrarily chose to solve this problem, assuming that the slow train was starting at 0 kilometers. But what if we put the fast train at 0 kilometers and the slow one at 8.5 kilometers? So let me grab my pen tool. So we're going to change our mathematical models, right? So our red fast train is now going to have a positive 25 meter per second velocity times time, and the intercept will be 0. And then our slower blue train is now going to have the negative velocity and the positive intercept. We're going to set them equal to each other just like we did before. 25t equals our negative 16.6 repeating decimal t plus 8,500. And when we combine like terms, we're going to get 41.6t equals 8,500, which we saw before. And that's going to give us a time of 204 seconds. Good news, we got the same time. We must not have done anything wrong here. And then we're going to substitute that into the red train's position time relationship. And I'm going to get 5,100 meters. And again, we got a different answer because that is from the red train starting position. So let's think about this. If our two trains are starting 8,500 meters apart, sorry, that's not quite as straight as I wanted to make it. Oops, I forgot the meters as well. There we go. 8,500 meters apart. And if our red train has gone 5,100 meters of those, then very clearly our blue train has made up the difference. So we're going to calculate that really quickly just to confirm. And there we go. So when we take that 8,500 minus 5,100, we're going to get 3,400 meters from where the blue train started, just like we did before. So the problem works either way, regardless of which train you choose to put in which starting position. So I hope you have found today's explanation of a very typical kinematics problem of objects with different velocities heading toward each other. When and where do they meet? I hope you've enjoyed it and found it helpful. If you have a video solution request for me to put on YouTube, whether it's an explanation of a piece of content or a problem to solve, you can email me at physicsproblemrequests@gmail.com. If you need some email assistance with a problem that you're working on, you can message me at freephysicshelpline@gmail.com. There is a limit of 10 questions per academic year. If you want to learn more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.